Thank you, Laura, for the introduction. So I don't want to give a talk that sits between you and lunch, but here we are. And also like the previous talks, I'm an academic researcher, but this talk is going to be half academic work and half industry work. So we're going to talk about a problem about gray failures in cloud systems, which should be a problem that's familiar to this audience. And gray failure is kind of so challenging problem that my research groups and the collaborators at Microsoft have been collaborating really on addressing this problem for more than 5 years. And so in this talk, we're going to give an overview of some of our work. And they cover both principles from those academic research projects and then how Microsoft actually integrate those principles into Azure at scale. And the solution also both involve some system-level solution and data-driven approaches. But we won't pretend that we have solved this problem. And so this talk, in the end, will conclude with some open challenges. So a universal way for how do we build system is to use clean abstraction. So system designer can abstract away the messy code details into uniform processes. And then we can introduce redundancies and then model this assorted kind of different interactions as some clean messages that we can exchange among different processes. And using this approach, we can build really large-scale systems that run on many, many nodes and that are fault-tolerant. But problem is, there is really a mismatch between this clean abstraction and software behavior in practice. So software today is much more complex than a process that's sending or receiving messages. For example, Cassandra process could have more than 200 live threads at runtime, and they are responsible for handle different requests, run many different background tasks, and each of them can experience some faults. And as a result, a process might appear alive, but is actually broken. And so this is essentially this problem of gray failures. And multiple recent studies have shown that this gray failure problem have been increasingly common in large systems, partly because of the scale and partly because of the complexity of the system that we're building today. And they can occur across many different software and hardware components in the cloud. And what makes gray failure challenging is that there isn't really one kind of dominating pattern among those problems. And there are many, many puzzling symptoms and root causes that developers have to spend a lot of time kind of trying to detect and diagnose these problems. So next, I'm just going to give you a concrete example. So this is a production incident that happened that involves gray failure that happened in Azure Storage Service many years ago, a number of years ago. And so the Azure Storage Service has a front-end layer that handles requests, and then a stream layer that stores the actual data in replicas among something called the extend nodes. And in this incident, there is some extended nodes, let's call it EN3, that's actually running out of free blocks. But somehow the stream manager was not aware of the situation. Typically it should, but there is some sort of bugs here. And because of that, when some request comes, and it can, and this stream manager will assign this EN3 to handle the request. And if this is actually a write request, it can cause this EN3 to crash. And at this point, the stream manager does notice the crash and will reboot the EN3. But then when this node comes back online again, unfortunately, this stream manager thinks now EN3 is healthy again. So it will be assigned to another replica set, and then the same fate just happens again and again. So after a while, so this stream manager does notice that this node has been just crashed for so many times, so it decides to finally remove this from production. But during this process, more and more nodes get affected, and because of the re-replication and fragmentation, which eventually leads to a cascading failure, basically. This here is just another kind of a concrete production gray failure incident that happens in a deployed Zookeeper service. And as many of you know, Zookeeper is a replicated service that's responsible for handling distributed coordination. And the leader is periodically sending heartbeat messages to the followers and for failure detection. And in this case, what's interesting that is the client that uses Zookeeper actually see many errors, but not all of the errors. Some of the requests can actually succeed. But during this time, the leader is actually happily just exchanging these heartbeat messages with the followers. And as a result, this pragmatic leader was just to remain the leader for a long time. There was no really leader re-election triggered. And so when the engineer actually checked the logs, there was nothing really suspicious. Similarly, the resource usage was normal. And if you use the Zookeeper's API, like this "Are you OK" API to query the leader, it will reply just "I'm OK." So what is happening here is that in this case, there is this serializer thread that's inside this leader process actually gets stuck because of some during its when it's dumping a snapshot to another follower because of a network error. But the serializer is actually holding a log when it's getting stuck, which in turn affects the request processor module. But the failure detect the heartbeat thread is actually not affected. And there's actually a fascinating story about how this failure was diagnosed. That was a talk given at SREcon 8 years ago. So if you're interested, you can check out this talk. So just to kind of quick show of hands, how many of you encounter problems like this? Maybe not in Zookeeper, but in some of the surveys that you have seen. Quite a few. That's good to know. But I know it's kind of a pain point in practice. So as the name suggests, this grade failure problem is really kind of ambiguous, has this ambiguous notion. And in fact, we asked many engineers about what do you think is really a grade failure. And as you can probably guess, there are many different answers. Some think it's just a performance issue. Some think it's a non-deterministic bug. Sometimes it occurs, sometimes it doesn't occur. Some would define grade failures as some sort of a fail slow issue or some increasing number of transient error in the system that cause reduced capacity. So those answers do capture some aspects of grade failure, but it's actually hard to really decide which one is right. And as an academic, we want to say, well, whether there's some more formal way that can define grade failure, and so that maybe more important, just to give us some thinking framework about how can different practitioners talk about this problem, and then also more important, get some insights about how to address it. So here's just an abstract model that we proposed of just how would you characterize a grade failure. So there is some logic entities of a system that provide some features, such as storage service or infrastructure, this VM services, network. And this system is going to be used by many different applications because this is in cloud environment and that has multi-tenancy. And those applications are also logic entities. They can be some web applications, some analytics application, or another system, or some users or operators. And now, because this system is a fault-tolerant system, there will be some observers that's basically checking whether the system is working or not. And based on the assessment, there will be also some reactor module that's going to take some actions to repair this system. So this is kind of the basic setup of how many cloud systems look like. And with this abstract model, one thing that's interesting that happens is because in this system, if you look at it, there are two things that are actually making some observation about the system. One is the observer that's built in the system, and another is the application themselves. When they interact with the system, they're also making some observation. So the interesting that really happens is when their observations differ. And we call this property basically a differential observability. And in fact, we would argue this is going to be really a fundamental trait of grade failure, is a form of differential observability. In particular, we can actually use this way of just how applications think of the system and how the observers think of the system, and we can actually find there's basically 4 different categories. And so, for example, if both the observer and the systems and think that, and every application in the system thinks that the system is working well, then this is in a healthy state. But if somehow the observer thinks that the system is bad, and also the application thinks the system is bad, this is also an easy case because this most likely is to some fail-stop issues. But if some application in the system actually like experience problems, but the observer in the system is thinking that the system is working well, then this is a form of gray failure. The last portion, the last kind of situation is when the observer may think that the system is bad, but in fact, all of the application on top of the system are actually not really reporting errors. And this typically happens because this is actually kind of a good form of differential observability, because this is typically meaning that the system has some fault tolerance mechanism that's basically shielding, masking the faults from the application. But the key thing here is the gray failure is occupy one quarter of this situation here. And with this model, it not only provides us with a way to really just define gray failure, but more importantly, we can draw some several principles from it. And first of all, kind of because the issue here is this really differential observability, so naturally we should really close this observation gap between the application and the observer. And this gap occurs because oftentimes the failure detector that we use in practice only look at just a singular aspect of failures, like up and downs, and we do measurements like measure the availabilities in lines, but oftentimes those singular metric is not really enough, and we really need like more these multidimensional signals. And I think when we're working on this problem, this is not really kind of a like very common thing, but gradually I think right now the many cloud systems are collecting many different metrics. So that's kind of a good thing here. Another aspect is if you look at this model, it's very tempting to say, well, maybe that's just to get rid of the differential observability. But in practice, this is infeasible, both because monitoring just so many apps is going to be very costly, especially at the cloud environment. And second, if you're monitoring many applications, it is going to go against the modularity principle. So instead, we do need to get some application views, but probably just which a more practical way is really just to try to approximate what the common application can see. And then the third kind of takeaway principle here is that the scale of the cloud is really the contributing factor for the rise of gray failure. But we can use the scale to fight the scale-induced problems. And in cloud system, because many components are making those observations, so and we can leverage them. But the problem is that those observations are typically made in isolation, so they only represent some partial view. So we need some solution that can break the silos and then can correlate those different observations. Another nice thing with scale is that once you have a large number of observations, you can also use them to address a common problem in practice, which is this blame game, which some components think is another component's problem, another component think is this component's problem. And then lastly, in addition to leveraging this kind of a spatial dimension, we can gray failure also oftentimes evolve over time. So correlating differential observability over time can help identify and pinpoint the problem. So next, I'm going to just present one system approach solution that follows these aforementioned principles. And in particular, traditionally, when we are detecting failures in large systems, we typically use some special kind of a controller, such as some managers or some monitors to measure signals like heartbeats or CPU usage. But based on the principle, what we think is the insight is that we should also detect what those requesters to a system are seeing. Based on this insight, we developed this new approach to detect failures by actually, we don't have to rely on some special components. We can basically take any component and then try to convert it to an observer, to an in situ observer, meaning that while these components are executing during their normal execution, we can gather some evidence. But those evidence is not going to be about those components themselves. This is going to be evidence about some other components. Of course, the challenge here is that we have this modularity principle. So oftentimes, the component it doesn't really have this incentive to help report errors about some other components. And This opportunity does exist. So if you look at, for example, more concretely some code in Zookeeper, you can see this. This might be hard to see, but basically, this Zookeeper follower, actually, if you look at the code, it has a lot of error handling logic, and those errors logs actually indicate problems about the leaders. But oftentimes those logs are just logged in locally. They're not really reported to indicate problems with about other components. But looking at this, one of the takeaways is that because this practice, there's a lot of error handling code in practice, we can actually leverage them. We don't really have to ask the developers to completely rewrite their code, and we can use some automated methods that can capture those evidence from the existing code. And this basically leads us to this solution that we developed. That's a framework that's called Panorama, which realizes this approach. So at the high level, what this tool does is it works actually in two stages. In the offline stage, given a component, it will try to analyze the source code of this component and then instrument the program so that we can actually convert it into an observer, even though that component itself has its own features. And then at runtime, when this instrumented components start to interact with other components, it will basically trigger some of the instrumentation hooks that we place there. And then once those instrumentation hooks are executed, they will be basically collecting observations about other components. And then all of those observations are going to be reported and into some centralized server that we can analyze and gather those observations. And so the key thing here is how can we actually convert some components to report errors about other programs. So this is basically a solution that we developed by using some program analysis techniques. And so the goal here is we want to, for a given program, we want to find some instructions in a program that can provide some error evidence about other programs. And typically those instructions are really often scattered around the source code. But we can use some systematic approach. Basically, we do do it in 3 steps that can identify them. So in the first step, we can identify, try to locate what are the code that cross different boundaries, and then we're going to extract the identity of what is an observer and what is the monitor, the subject. And the last step, we're going to find what code is actually influenced by this observation boundary code. So due to the time need, I'm not going to dive into the detail of each step, but I'm happy going to talk about these details offline. So just a kind of quick show of taking this in situ observer approach, going back to the Zookeeper failure that we showed, once we actually placed and instrumented these observation hooks in Zookeeper, this graph shows what's happening is we can actually these panorama observers can start to report the failure very soon after the failure occurs. And just to providing a baseline of what the client is actually seeing is this lower figure is showing what the client is seeing. Basically, these cross are showing the timeouts that's reported by the client. So you can see these observers are actually closely approximating what the client is doing. But also know that if you look at the client's view actually is pretty noisy because it's executing some mixed workloads. So even during the failure time, a lot of the clients are actually reporting error success. So you can't really only use the client's view here. And one of so that's in terms of the detection capability. One potential concern you might have is what's going to be the impact because we are converting a component into an observer. So is that going to be costly to the component? So performance-wise, there are multiple operations that Panorama would do, but the key operation that can potentially influence in a component is this report async hooks that we place in the component. And typically, we did some micro benchmark, and it typically only just takes less than 1 microsecond, and because this is actually done asynchronously. And we also measure just the overall end-to-end latency impact to the observer, and the average latency is actually below 3%. So this is kind of just the system-level solution. So in the following talks, I will hand over to my colleague Ze, who will talk about how Azure apply these principles.
Sure, yeah, thanks, Dr. Huang. So yeah, in the following talks, I will talk about how we just apply such kind of awesome like a differential observability model into our like a Microsoft Azure AIOps design. So this case study, right? I mean, I will show 4 case study to demonstrate the 4 principles in different angle. It only touched a small corner about the problem, but hopefully by just showing this case study, we can trigger more thoughts, right? How we can apply this principle into a large scale real world problem and systems. So before that, I want to talk about what we are doing, right? In Microsoft in terms of the AI ops. So we have been collaborating with industry other partner and also academic partner like Dr. Huang on solving the problem, right, to apply the AI for system design, for DevOps improvement, for like customer enhancement. For example, like say AI for system, we are doing like VM provisioning optimization. We are doing like a host resilient optimization using like a multi-banded reinforcement learning, trying to make it smart. We are trying to using AI to do the disk failure and memory failure prediction, and also doing like a sport VM optimization, harvesting optimization, something like that. And AI is also using in like a DevOps lifecycle. For example, we are using AI to make sure the deployment are safe, the change management are safe, and also we are doing anomaly detection to find the grade failure, find different other kind of problems actually in the cloud before it really become a news in the whole world. And also we have like a host governance, right? Health governance to monitoring the memory, CPU is another kind of like a problem that is very hard to solve. So we actually published a lot of paper, right, in the other kind of like USENIX conference. If you are interested in those topics, you can go to those like conference to find more information. And we can also chat offline on those topics as well. So when we apply the differential observability model in Azure, right, we need to follow certain kind of like steps. So the way we are follow is kind of a data-driven step because the Azure is really high scale. So what we are doing is like we trying to collect the data, right, observability from different places, and then put them into a centralized like a corpus. And then we are trying to dig the insights from data in an automatic way using detection, diagnosis, prediction, and optimization. And then those insights will automatically trigger a lot of like actions, like a stop bad rollout, right, to do the online repair, to do the mitigation on the fly, something like that. And all the things will be formed as a feedback to the original data. And then let the whole loop keep on going to let it optimize by itself. Okay, yeah, it is some pictures I want to show about like what the real like data center it is. So it is a data center actually in Washington State. I think it's in Quincy. If you look at the scale, right, of the cloud, you will see a small car, right? Compared to the like a data center with their car, you can see how big it is. So right now it's like, yeah, by showing the picture, I just want to demonstrate that actually right now for such a data center, right, or region, like Microsoft had more than 62 regions and more than 200 such kind of data centers. And the number is growing year over year. And because of the scale is large, and even, I mean, the software, right, I mean, in each data center, or on each like a node, right, is also huge, right? We have like drivers, or we have different like hardware vendors on different layer from the node level, cluster level, region level, even just like in the above ARM level, there are a lot of like complex like interaction between different components. Even the vendor, right? Different vendor will also bring certain kind of like heterogeneous problem into the cloud. So the first case study I want to show is like how we are like trying to apply the closing the observation gap kind of like principle in one of the problem we are facing is how to like really to understand the gap between the guest inside and the host inside. right now, a lot of cloud providers or like a system engineer, right? When they look at monitoring their system, they are only care about, okay, if my machine, if my component is healthy or not, right? Usually they think, okay, the service like owner, right, or like Cassandra, like from some company A, right? They are running some Cassandra in Azure, right? We think like the Cassandra owner are only there like monitoring for the Cassandra service, but such kind of independent of monitoring bring a lot of like gaps. For example, when we are doing some operation on the infra level, a lot of time we do not know what exact impact is happening for the Cassandra. For example, let's say we are deploying a certain kind of impactful rollout right on the host, and then it frees the maybe NIC car actually for like 1 second. What exact like impact this 1 second freeze on the host will impact the Cassandra read and the write timeout is unknown. So because of the gap, it just like take a longer time for us, right, to mitigate the customer reported issue, and also it take a much longer time for us to recover the SRISO regression that's caused by the infra. And also, we are just like always like when we receive a customer support ticket, right? I mean, when we on call, the first thing is we need to figure it out whether it is really a customer, their own issue, it's a false alarm, or it's really our infra issue. So it actually, such kind of like independent monitoring bring a lot of such kind of gap in the whole like on-call or like SRE life cycle. So the solution actually we are looking for is really to incorporate the guest insights into the whole host diagnosis by applying the like closing the observation gap principle. So so right now we are actually release certain kind of like a REST API, right, to empower the customer that actually can report their service impact directly into the Azure. So that actually we have a certain kind of like a AI model and a pipeline to ingest those insights into our internal correlation engine to automatically to correlate the reported impact with the host side failure we are observed. And then we can take immediate action, right, based on the impact to verify, okay, what we are observed on the host is not a red herring. It is real issue that are actually causing a lot of pain to the customer. And then we can do the mitigation on the fly or prioritize the mitigation for those host issue. Or we can stop bad rollout, right? Usually we know that actually the rollout, the change also always causing problem. I mean, from different angle. Okay, the other case study I want to show is like how we are applying the approximate application view this principle into our like daily operation. Also, we know that actually guest insight is good, right? It's awesome, right? If we can just like get the guest real service telemetry and incorporate it in the host, then it can really help us to increase the like customer's experience. But the problem is like because of the compliance issue, right? I mean, we cannot like install certain kind of like agents within the VM to pick the like customers like workload pattern, right? Because a lot of like security or compliance policy restrict you to that. Another thing is like some customer maybe they do not know how to use the like kind of like API to report their impact into the host. And a lot of time, actually, even we just like for our like first party application, right? Even when we install some kind of like a monitor within the VM to monitoring service, it is really use a lot of resource of the guest VM. So we cannot like collect all the telemetries, right? We are designed to collect within the VM. So we need to approximate, right? Really what the guests are feeling with the guest host level observation, because we are from the infra side, right? We know what happened on the host. Then we are trying to just like really understand the gap between these two. So it is one example that actually we are just like applying in our daily operation. For example, when we like release a new like agents on the host, we deploy it out, and then we are just like to monitoring the like the guest observation from our side. For example, based on the previous, like the first principle, right, close the observational gap principle, we already learned how does the host level network freeze will impact Cassandra's read time and like a write timeout. And then we build such of a mapping between the application level and the host level. And then when we roll it out, we build our own SLI for the host level rollout to make sure, okay, the P99 of the host rollout, right, that actually, the delay that actually introduced is less than the SREcon we had defined earlier. The third case study I want to show is how we harvesting the temporal principle, pattern this principle into the whole, like into the Azure. So the case actually we are showing is we are using a memory leak, this case. So as we know that a memory leak is notorious in cloud, right? It causes a lot of great failure. For example, let's say we are roll out some like change on the cluster. Maybe that like a change in the agent, right? It will leaking the memory in the user mode or in the kernel mode. Such of leaking usually will causing like performance degradation, the host reboot, or the VM allocation failures. It's a very challenging to really to detect such like a memory leak or CPU jitter kind of problem in the cloud, because in the cloud we are running very dynamic workload, right? I mean, those dynamic workload will have like a very dynamic like a CPU and memory usage pattern. So it is kind of a noise, right? That actually generating in the cloud that for us to detect the leaking pattern. So the existing approach definitely we are using right now in cloud, definitely there are two ways, right? One is a static approach. The static approach is trying to using some tools, right? Like memory leak analyze tools to analyze the code to find the potential like a memory leak code that actually that is very dangerous, and then we're trying to fix it. The second approach definitely is kind of a dynamic approach. We are putting some instrumental code into the program, and then trying to monitoring the memory usage over time. But it's not that it is quite intrusive and also have like a certain kind of high overhead if we just put a lot of instrumentation into the code. So I mean, we published a paper in OSDI like 2 years ago, right? The new approach we are trying to use is called Resign, this project. This one is trying to exploring the temporal pattern of the whole memory leaking pattern, and then trying to separate the detection and the pinpoint problem in a different stage. And then even in the detection stage, we decompose the detection into multiple stages, and then to look at the detection into a different angle. And then we have a centralized system to oversee the whole detection, and then we trying to detect it and diagnose it. So it is a whole overview of the Resign in this project. So basically, when we in the detection stage, right, we are looking at all the hosts together holistically, and then we will fail alerts when we find there are certain kind of memory leaking holistically in the cloud. And then we pick up certain kind of sample node to automatically to run some diagnosis and to do the mitigation on the fly. So this slides show that actually how we doing the anomaly detection. So the anomaly detection we are doing is kind of like a bucket-based pivot analyze. So we break down the host usage, right, for individual components to different bucket, like a 15 megabyte usage, 100 megabyte usage, 200 megabyte usage kind of bucket. And then we just to count, okay, how many hosts in the cloud that actually is falling into those bucket, right? And then we monitoring each bucket actually closely. And then to compare the number of nodes in that bucket with the baseline. If there are certain kind of bucket has certain kind of anomaly outlier, right? And then we are sending alerts, say, okay, looks like for this agent, right, on this bunch of nodes, they are like have an increasing memory for this bucket usage, right? And then later on, we will just like to capture the heap snapshot, actually for those like leaking bucket, and then trying to find out, okay, what kind of like a real issue is causing the memory leak based on those like a heap snapshot. So this service has been running in Azure for like 5 to 6 years already, and then it's really changed the game that actually for our like daily operations. You can see that actually after we apply that model, right, the VM reboot caused by the like memory leak is reduced by 41 times, and the VM allocation failure is also reduced significantly. So for more information or more detail, right, we can chat offline, or you can go to the OSDI paper, to resign this paper to check more details. Okay, the last case study I want to show is how we leverage the power of the scale, right, using safe deployment as a case study. So I mean, deployment, I mean, as a like SRE or any like system engineer, definitely know that actually is one of the most challenging work for a large scale system, because majority of the issue, right, in the cloud is caused by the changes. No change, no problem, right? And the reason why it is so difficult to do this deployment, right, safe deployment in a large scale system is because, I mean, we have a lot of microservices, right, in the cloud. They are on their own CI/CD pipeline. They are do the independent updates, right? And then if there are issue happen on certain kind of like a node or region, right? The customer like send a CI come in, right? Given so many change happen on the fleet already, which one is really causing this problem, right? Which change is really cause this problem? It's really a very tough problem. The good things is like, okay, Azure is very big, right? I mean, there are more than 62 regions, there are 200 like data center. Okay, let's leverage the like kind of like the first principle, right? To explore the like scalability principle. Let's do certain kind of like safe deployment stage by stage. So the first step we are trying to make sure the deployment is safe is by leveraging the scale of the Azure. We roll out the code, right, to like a staging or testing environment first, and then we baking for a while to see if there are any regression, and then we move on to the canary. And then we baking for a while, and then move into a pilot, right? And then we just like do some spatial and temporal kind of analyze to really to make sure that actually the change is like stable actually in each like safe deployment stage. And then the reason, and when we choosing the stage is also there are a lot of like statistical optimization here, because a lot of like bug, right, is triggered by some workload or certain kind of special hardware. When we roll it out, we also smartly choose, okay, what kind of region may have certain kind of workload characteristic, or what the other region has certain kind of hardware characteristic. We are trying to make sure that actually the deployment actually we cover in the early stage can fully like cover all the like corner cases we are facing that actually historically. After that, right, after we break down the deployment into different stages, right, leveraging the large scale of the Azure, and then we have a lot of like local watchdog on this cluster to monitoring the like health of the node, the host after deployment. But there are certain kind of like drawback of this approach, because a lot of times such kind of local watchdog is threshold based, because we cannot design very complex watchdog within the host. It will consume a lot of like resources of the machine. So and then another problem of the local watchdog is like if there are multiple changes happening within the cluster scale is too small. It's very hard for us to do the attribution, to look at the problem like in a global view, holistic view. So we just like design, just based on the principle, the differential observability principle, we are designing another layer above the safe deployment policy, local watchdog. we call it as a global and intelligent watchdog. So what this is doing is like look at the issue happen on different cluster and the regions holistically, and then we are using certain kind of like a AI model, right, to like trying to do correlation and to do the decision making. So for more detail, you can refer to the Gandalf paper in NSDI we published like 4 years ago. So the idea is right to leverage the scale of the cloud to do the before and after analyze, to do the spatial and temporal analyze, and then to do the exponential decaying analyze between the failures and the rollout, the changes across the cluster and globally, and then to understand what is the relationship there. So after we roll it out, we can capture majority of the issue, right, in the early stage, like a stage, canary, pilot. Maybe it leaks certain kind of issues in product, but usually we can capture it in very early stage in production. The reason why we are leaking some is just because certain kind of workload is really very special. I mean, the customer, they are running very weird special that actually we did not reproduce it in the pre-product stage or early stage, but it is a feedback loop, right? When we learn it and then we just like apply those like testing in early stage. So right now the issue in production is getting smaller and smaller. Okay, so yeah, I've done all the like case study sharing. So I want to bring up some open challenges here, right? It is some problem we are still working on. It's not completely solved. The major cause of this such kind of open challenge is because of the hyperscale. The Azure is too big, right? I mean, there are so many vendors, there are so many like hardware SKU, VM SKU, and then we are need to serve so many customers with very diverse like workload characteristics. And then how to log. The other one is how to do the right logging, right? There are so many components, there are so many drivers. How to like log at the right time, right? Because from our experience, 90% of the like logs actually are information log is useless, but it's used of a lot of like computation resource to process those things. We need to improve the logging. We need to make sure, right, the gray failure is not happened using some preventive like measurement. Right, how to prevent the gray failure happening. And the last thing is the noisy label, right? A lot of time, actually, the issue is happening is not on this service. It's just because you have some noisy label shared on the same host. How can we quickly identify and attributing that is also another big challenge for us. So conclusion. So in this talk, we are talking about the basic key traps of gray failures in differential observability. And also, we see that there's no single silver bullet to actually solve all the problems. And then there are 4 principles that is very, very valuable, right, to trigger you to think how you design your reliable system. And then we need to use both the system and the data approach to solve the problem. Yeah, that's it. I think go to the QA session. Yeah.